in situ measurements? And the answer is yes. So that's what's been done before, and so alternatively you can basically use the correlations that are developed directly going from in situ measurements to the settlement. And one example of that is the Berlin and Burbridge 1985 equation that we use in this class for primarily for calculating foundation settlements in sand, and we'll discuss it in a couple of pages from now. It starts on page 12. Any question? All right, so let's flip the page to page 12 now. And again, we're going to have a few pages on the settlement on sand and then a few pages on settlement on clay. So, page 12, SPT-based method for settlements in sands based on Berlin and Burbridge 1985 equation. These are the equations that are made based on case histories. So they use over 200 case histories to come up with this correlation. All the foundations were designed to have a factor of safety of 3, which is what we usually use. We usually design foundations to have at least factor of safety of 3. They're developed for quartz sand, so you can't use it for other types of sands. But that's not too big of a limitation. Usually if you get to carbonate sands, you're in a much bigger problem. You want to do a very elaborate lab testing. And we don't really run into those issues onshore. So for building, most of the structures that you build onshore, they're quartz sands, but the carbonate sands become an issue when you go towards offshore foundations. In this case, foundations can be embedded. So the embedment depth is D. So this is the shape of the foundation. Load Q is applied over here. It's sitting on a foundation with the dimension B. The embedment is the distance from the ground surface to the base of the footing. That's D. And the distance from the base of the footing to the bedrock is called H. So it's not. So it's a general case. You can have embedment D could be 0 or non-zero value. You can have H, so your bedrock does not have to be infinite. You can have a bedrock encountered at depth H. So it's a more practical case that we run into. There are a few variables that are defined on this equation, on this plot on the right side. So that's the embedment depth. QB is the unit load due to structural load plus footing and backfill weight. So the load that you use in these equations as QB is the weight of the foundation, weight of the structure, and if you're going to backfill on top of the existing, so if you want to fill this area with a backfill, which we may or may not do, but in some cases you may end up doing, you have to add that load on top of it too. So basically, all the loads that are applied at this dotted line elevation, okay, everything on top of that, those are QB. And then there are these other two depth variables too. So Z is defined from ground surface, ZF is defined from the base of the footing, so keep those in mind too. And then the equations are right here. Settlements are defined using these three equations. So W, which is the settlement, divided by LR, and LR is nothing but a reference unit, so it's just to make sure the units work. So if you're doing your calculation in SI unit, you replace LR with just 1. If you're doing it in foot unit, you replace it with 3.28, and if it's in inch, it's 39.37. It's just to make the units work. And we have three cases, three equations here, and I'll go through what those mean. But we have for normally consolidated sand, so this is normally consolidated sand, use that equation. For over-consolidated sand that starts OC and ends NC, so it starts over-consolidated and ends normally consolidated, you use the second equation. For overly consolidated sand that starts OC and ends OC, we use the third equation. So this should remind you of a lecture that we had in soil mechanics, where we were discussing the same stuff. We had case 1, case 2, case 3 for consolidation settlement. But that one was in a different soil, right? The consolidation, we defined consolidation in clay, not for sand. So what is this about this equation here that we are defining NC and OC for sand? And I'll talk about this in a little bit. So we have these three cases, very similar to the consolidation cases in clay. Let's go through all these variables. So there's an Fs, Fl, Ft, and I sub C, and those are all defined here. There's B, which is the foundation width or dimension. There's QB, your load. Then there's that PA, the 1 atmospheric pressure right there. So PA is just 1 atmospheric pressure. Depending on what unit you use one of those numbers. Fs is the shape factor. All the definitions for all these are outlined in the next page. But Fl is the layer thickness factor. Ft is the time factor. So how much settlement you get right after the building, and how much right after the building is built, and how much extra settlement you get 30 years later. So that Ft is supposed to take care of that. I sub C is the compressibility index, and I'll talk about that later. QB is your bearing pressure. Again, it's a structural load plus footing, the foundation, and if you have backfill rate, you add that too. And then for this case here, you see we have that parameter right there, sigma prime Vp at Zf equal to 0, and that's defined here. That's a pre-consolidation stress at the base of the footing. So before you add the footing, the pre-consolidation stress at that elevation. And that elevation refers to Zf equal to 0. That's Zf right there. So basically, that dashed line is what we are talking about. Okay. Any question before we start digging into all these variables? Yes.
So the problem has to kind of specify whether you're going to backfill the foundation, because that value, that sigma prime V sub P is going to change, right?
That is, well, it's your QB that changes, and that will change. No, it doesn't change the sigma prime Vp. Sigma prime Vp is before you excavate to build the foundation. So the backfill was already there. You excavate it, so then the stress goes down, and then you build the foundation, you put the concrete on, you put the structural load on, and you may or may not add the backfill on. So then your stress goes from, let's say before you start building the foundation, let's say your stress was 10, and then you excavate it, so your stress goes to 0, and then you add 60 load on, so now it goes to 60. And that 60 depends whether if you're backfilling or not. Your sigma prime Vp is pre-consolidation stress, so it means the 10 that was before you started excavating.
Gotcha.
Any other question? Maybe we go through the variables, and that might, I'm sure you'll have more questions when we get back. Okay.
Actually, I have a question.
Yeah.
You said that all foundations were designed for a factor of safety greater than 3. This doesn't have any factor of safety built into it in this equation, though, right? That's something you would apply afterwards?
So your QB has the factor of safety in it. Because that's your structural load. When the structural engineers give you the load, they either give you the factor of load or the net or the on-factor load. So that's where the factor of safety comes in. But the factor of safety that is, I don't want you to get bogged down with that 3 because we talked about the factor of safety for foundation design next week when we talk about bearing capacity. That's really where we talk about factor of safety. And that's 3 in that bullet item refers to the factor of safety against bearing capacity.
Okay.
Yeah. Any other question? Alright, so let's flip to page 13 now. And let's get to that comment on NC and OC sand. So again, we define normally consolidated or over consolidated usually for clays. But it turns out that sands could be also normally consolidated or over consolidated too. And it usually doesn't matter, except that in settlement calculation it does matter. So what does it mean for a sand to be normally consolidated? Let's go through all these bullet items here. NC sand settles more than OC sand. So if the sand was loaded before and that load is gone, then that sand is a little stronger, so it settles less. But if it wasn't preloaded before in its past history, then it settles more. So the NC sands settle more than OC sands. Similar concept as consolidation in clays. But how do we decide if it's an OC sand? How do we decide if it's over consolidated sand? One way is to infer from geology. So the geologists might come and say, well, this area was under glaciers, so it was loaded before, now that glaciers are gone, so these are everything underneath here, whether if it's sand or clay, they're OC. The third bullet item is, you know from the history, possible fill and or excavation in the soil. Again, the same concept. You know that there used to be a Walmart here, and that Walmart is gone, so you know that everything underneath that foundation was preloaded. So whether if it's sand or clay, those are going to be over consolidated because they were subjected to some large aerial load. Now let's go to the second item. Infer from consolidation test on clay layers. If the clay interlayered in sand are OC, it is inferred that there has been a large load on the site in the past. So usually in sites we have sand, clay, sand, clay, sand, clay. So they're interlayered. And what do we do the consolidation test on? We do it on clays, right? So we get a sample from that clay, we bring it to lab, put it in the consolidometer and test it, and then we know if that particular clay was over consolidated, and we can know even what over consolidation ratio it's under. So if you have a sand layer that is sandwiched between 2 clay layers, and both of those 2 clay layers are OC, would that tell you that that sand layer is also OC? The answer is yes. So the reason we are doing this is that we can't do the typical consolidation test on sand. It doesn't work. But we can use the data from the layer on top and below that sand layer to know that this sand was subjected to some large aerial load in its past. Does that make sense? All right. Now I like this last item here. Assume NC if you're not sure. So if you don't know if it's OC or NC, it's always conservative to assume that it's NC because an NC sand settles more or less compared to OC. It settles more, so it's more conservative to assume that it's NC. Any question? All right. Now we get to this interesting one, the compressibility index, I sub C. And I want to make a comment here not to confuse this I sub C with something that we had for CPT. Remember that soil behavior ratio, I sub C, for CPTs that we used to know to find the type of soil for whether it's sands or clay or gravel based on those zonings. This is not the same I sub C. Okay, so don't confuse it with that one. And it comes with this equation. So researchers looked at data of I-sub-C versus N60 bar, and N60 bar is the N60 values average over the depth of influence, or ZF0, below the base of the footing. And I'll talk about what depth of influence is, but before getting confused of that, N sigma bar is basically the average N60, or I'm sorry, N60 bar is basically the average N60 below your foundation, over the depth that you think is more reasonable. So we'll talk about what depth is reasonable for that. But if you look at this equation, as N60 increases, I-sub-C decreases, right? I want you to go back to the equation for elastic solutions and tell me what parameter in that equation is this I-sub-C supposed to replace or represent. So go back to page 6 where we had the equation for elastic solutions and look at all those variables that we had there and see if you can find the same variables in the equation that we had based on Berland and Burbidge 1985, and try to find what parameter this I-sub-C represents. Again, I want you to look at these equations from, like, zoom back and look at the bigger picture. Because I gave you the Berland and Burbidge equation, but you can find tons of other different equations in literature. So don't get lost with specific equations. Try to find the common variables and understand what settlement should depend on, and try to find those variables that are common in all these equations. So in the elastic solution, what page is the elastic solution? Page 6. So we have QB in the elastic solution. You see QB in the Berland and Burbidge equation. Yes. Okay. So QB is checked. There are a bunch of variables that, so I'm going to put the elastic solution side by side here. Okay. So this is the elastic solution. And let's have page 12 here. So put page 6 and 12 side by side. And let's look at for simplicity, let's look at the first equation on page 12. So for normally consolidated sand. W QB, B in denominator, B in denominator. Bunch of factors, shape factor, L, what is FL, layer thickness factor, FT is for time. So FS, FL, and FT. Can I lump those in those I1 and I2? That's basically what they are, right? The I1 and I2 are the influence factors depending on the geometry and Poisson's ratio, blah, blah, blah. So all those are covered. The only one that is not covered is this I-sub-C, which is related to N60. So you can use in situ test to estimate it. And what is the parameter that we haven't covered on the elasticity yet? Elastic modulus, exactly. So going back to right before I started talking about the page 12, I said one alternative to using elastic solutions or one alternative to use the in situ test to get the elastic modulus to plug it into elastic solution is to go from in situ test directly to the settlement equation. And that is done by these guys who developed this equation. They added this I sub c here to represent the elastic modulus in this equation. So technically, if your sand gets stronger, I sub c should reduce, because I sub c is in the denominator here and E is in the denominator, so they should be, if E increases, I sub c should decrease. And you can see that in the equation that we have on page 13. So if you look at I sub c here, if your sand gets stronger, your N60, average N60 below your foundation should also increase, and that will reduce I sub c, and that will reduce your settlement. Okay? So again, do the same thing when we get to the clay equations too. I want you to compare everything to the elastic solutions and try to find those key variables. Okay? Any question before we move to the next one? Alright, so we said I sub c is based on N1, is based on N60 bar, and N60 bar is the N60 value average over the depth of influence, or ZF0, below the base of the fluid. So how do we measure depth of influence? What is depth of influence and how do we measure it? Well, obviously we measure it with this equation. So ZF0 is LR. Again, LR is there for units, so if you're doing it in meters, you can cancel out LR. It depends, it's dependent on B, the width of the foundation. Has that funky exponent over there, but don't get confused with the power function, but it's basically related to the width of the foundation. Now I want you again to go back to the elastic solutions and point at figure that is supposed to give you an idea of what this influence factor, depth of influence is. Let's flip back to the elastic solutions. Do you see it? It's on this page, so can you spot it on this page? It's this one, right? I sub z, the influence factor. What is that figure telling us? How do we use I sub z? We use it, it shows up in that vertical strain equation, right? Right there. Strain equals QB divided by elastic modulus times I sub z, and then somebody integrated that strain and came up with the settlement equations. So strain depends on I sub z, and I sub z is plotted here versus depth. And this figure tells you that by the time you get a lot of strain right here, a lot of strain. And by the time you get to this step, so the vertical axis is z over b, below this point is very little strain. So this is telling you, this figure is very important. We don't really use it in a sense of calculating values, but it has a very important conceptual value here. And that it's telling us that a lot of your strain, if you have a foundation sitting on a soil, a lot of strain in soil which results in settlement occur in this range. Roughly z over b of 1, which then if you multiply by b, roughly 1B. Okay? And by the time you get below 2 dimension deeper, the effect of the load is gone. You don't get that much strain. And if you're in charge of specifying the site investigation scope, and you want to tell the contractors how deep they should drill, what depth would you pick, you would probably tell them to go, 2 diameter or 2 dimension deep, because beyond that, it's really not that important. You don't really care if it's soft or strong soil down here. What you really care is what is it right there. And that's 2 times foundation depth. 2 times foundation dimension depth. And most of the strain occurs right here. So about one foundation dimension. So that is why if I go back to page 13, the folks who developed these equations said, well, we want to have I sub c that estimates the elastic modulus, and we want to relate that to N60, but I don't want you to use the N60 that is really deep, that is not going to affect your foundation settlement. I want you to get the N60 that is representative to the area where you are getting most of your settlements. And that is how they came up with this depth of influence. So if you get rid of the LR, which is the unit conversion parameters, the depth of influence is basically equal to B to the power of 0.79. And forget about the 0.79, it's almost basically ZF, or depth of influence, is almost equal to 1 foundation width, or 1B. Okay, so that is in line with that figure that we just discussed, that you get most of your settlement in that 1B deep below your foundation. Is that clear? Any question on this? All right, so that's the depth of influence. We have these other factors, the shape factor, Fs. It comes with this equation. It's a function of L and B. Again, L is always the larger dimension of the footing. B is always the smaller dimension of the footing. So if you're a square footing, you get 1. If you're a strip footing, L over B is really large, and then that gives you 1.55. Layer thickness factor, that's FL. It depends on H, and just to remind you, going back to page 13, H is the depth, is the distance from the base of the footing to your firm layer, or the bedrock. So this is your bedrock. So that depth is H, and you can use this equation here. It's based on H greater or smaller than the depth of influence. So if your H is larger than depth of influence, that factor is 1. If it's smaller than depth of influence, that factor becomes something smaller than 1, because you're hitting bedrock too soon. You're not going to get that much. Your settlement will be reduced, because this factor will be smaller than 1. And then we get to the time factor. So it turns out that even if you're in sand, you get a little bit of consolidation type settlement, which means over time you get this extra settlement due to creep and a little bit of consolidation and a lot of different factors that we just lump them into this term called time factor. So what that means is that you have a new building, you build it, you get 2 inches of settlement right after all the load is on the building, and then over time, after 30 years, you get another extra 1 inch of settlement. So total settlement would be 3. This time factor takes care of that. So Ft is 1 plus R of 3 years plus R sub t times the log of t over 3 years. So the t right there is the time in years. So if it's 30 years, you put in 30 over there. R 3 years is this parameter here. That's the ratio of settlement developing over a period of 3 years to the immediate settlement. So these are all given, or we can make assumptions. R sub t is the ratio of settlement developing over a log cycle of time to the immediate settlement. So for static loading, R 3 years, you can use 0.3. R sub t, you can use 0.2. So for example, if your T is 30 years, if you want to know how much extra settlement you get after 30 years, that gives you F sub t of 1.5. So what does 1.5 mean? It means that if your immediate settlement was 2 inch, how much extra settlement are you going to get after 30 years? So your total settlement after 30 years will be 1.5 times 2 inches, which is 3 inches. So immediately you get 2 inches, and then after 30 years you get 3 inches, which means the extra settlement that you got after 30 years is 1 inch. Right? So this gives you the total settlement after 30 years. If it's a fluctuating loading, those factors are a little higher, because if you have a dynamic loading, can you give an example of a case where we have fluctuating loading?
Like a warehouse facility?
Warehouse facility, right? Any mechanical instrument or anything, any foundation that is bearing a load that fluctuates, that is a dynamic load. It could be a foundation for a mechanical instrument, it could be a foundation for probably warehouse foundation is somewhere between static and fluctuating. Fluctuating loading is something that keeps loading and unloading with a frequency of, say, like one second. So the load keeps going up and down in 1 second. Warehouse is, it's not static load, but it's not as dynamic as mechanical foundations. So these parameters will be a little higher, and after 30 years, that T is 2.5. So again, the same example that I just said. If your immediate settlement is 2 inches, how much extra settlement you get from a fluctuating foundation after 30 years? How much? 3 inches, 3 extra inches, right? So 2.5 times 2, that gives 5 inches total, which means your immediate settlement was 2. After 30 years, you're 5. So the additional settlement that you get due to this loading is 3 inches. Question?
Yeah, regarding the fluctuating load, is there some sort of, maybe I missed what you said, what's the actual parameter to determine whether you're talking about static or fluctuating loads? Is there some sort of range of the amount of weight that's causing any type of over-consolidation, or?
Yeah.
I'm just curious how you're going to determine, well, this place is a fluctuating load because why?
So I'm sure there are. The more academic way of finding that answer is to go back to the Fairland and Bearbridge study and see how they define fluctuating load. But for engineers, when I hear fluctuating load, I immediately assume a mechanical instrument foundation. So a foundation on any instrument that has frequency of loads about 1 second. Stuff that the loads are more than a couple hours frequency, I wouldn't call those fluctuating load. I would just assume those are static load. But just like anything else in engineering, if you end up designing a foundation for something that you're not exactly sure if it's fluctuating or static, I would probably make a conservative assumption and use the fluctuating parameters. I'm trying to think of a good mechanical instrument that needs a foundation design. Can you?
Would a windmill?
A what?
A windmill? Would that count?
Yeah, that's.
What a roadway.
Yeah, roads and bridges, I mean.
So roads and bridges again,
Where you would go, but then
we
you have
wouldn't, I've never assumed a bridge load to be fluctuating, although I see the point.
Is that a situation where the loads are fluctuating, but the amount of load relative to like the structure or the engineering for the weight is essentially inconsequential or small enough that you can neglect it?
That's a very good point too. So you have, for most structures, we have a dead load or a static load that doesn't fluctuate, and then you have a portion of the load that does fluctuate. So then the question becomes, do you have 10 kips of static load and 10 kips of dynamic load that is significant, or do you have 100 kips of static load with 1 kip of dynamic load? In that case, it's just not gonna, doesn't matter really. So let's say, just for an example, let's say we have a case where we have 10 kips of static load and 10 kips of dynamic load. Then you can break your settlement calculation into 2 pieces. And for the static part, you can use the static parameters, and for the dynamic part, you can use the other one, and you can superimpose them, add them together. Yeah, when this equation, I've never used it in practice, and partly is because I think this part of the equation is usually used for, again, mechanical instrument foundations. For a lot of dynamic loads that we deal with, like stuff that we design for earthquakes, anything seismic related, bridges, it's a whole different set of way of approaching it. So we don't really lump the dynamic component into these kind of settlements. We tend to